Hi students. Okay, so we are in part 2 of chapter 8 as we continue with the introduction to hypothesis testing in Psych 218, analysis of behavioral data. So last time in part 1 we talked about what hypothesis testing is, the logic of hypothesis testing and why we do it, as well as the steps we use for hypothesis testing, steps 1 to 4. So now that we've done the steps, we're going to continue with looking at the ways that we can make certain errors in our decision when we do hypothesis testing. And so we continue with slide 23 in our lectures, slide used here. And we start with uncertainty and errors in hypothesis testing. So remember, the steps we use is to help us find a way to compare the sample, specifically a sample mean drawn from the population from the population distribution, or specifically a sampling distribution of sample means that is meant to represent or approximate or estimate the population. So once we have set our critical region after stating our hypotheses and gathered our data and got our test statistic and put that into this null distribution, which is the sampling distribution that assumes the null is true, and we make a decision. However, there are times where, even if the sample mean seems so extreme, it turns out it comes from the same population on the day of the test. So we would say something like, we decided there was a difference based on the evidence, but it turned out there was no difference between that treated sample and the population from which it was drawn. So what the slide says here is that because hypothesis testing is inferential, that is, we make inferences and it's part of inferential statistics, we start off with limited information from the sample. So remember from the last chapter, chapter 7, where we talked about sampling distributions and why we do it and how the sample size directly affects our standard error. That is the standard deviation of the sampling distribution of means. And so unless we grab everybody from the population, and even if we grab population minus 1, it is limited information from a sample. And so we must make a decision based on the sample, but we must be aware that our information is limited, and therefore our conclusions and inferences has a chance, a probability of it being incorrect. Therefore, because we are working with limited information to make general conclusions or inferences, errors are possible. So that's what the second point is saying. So it would be like trying to pick one person from 100 people. Let's say one person's hiding a special prize that if you pick the right person, you would get the prize. There are game shows that use this concept, like in North America, there's this show called Deal or No Deal, where you would pick from many boxes, and one of those boxes would have $1 million. And other boxes would have either smaller prizes, or it would just have things that tell you, oh, you lost the game. And you have ultimately one box to choose from that is the maximum prize. So because we don't know which one has the box, just like we are grabbing from a sample and we don't know everything about the population, we can make errors. Here, the error is not sampling error, it's a decision error. So sampling error is sample bias because the sample we get is not population data. So because we have sampling error, we could also make decision errors or inference errors once we engage or once we do hypothesis testing. So there are two types of errors that we can make, and we have mentioned these before, particularly type 1. So in the next 3 slides, you see type 1 error, type 2 error, and a decision-making matrix where there are 4 possible outcomes, where you make 2 decisions, whether to reject the null or fail to reject it, and depending on your decision and what happened on the day of the test, the moment you collect the data and test it, your decision could be correct or incorrect. So first, let's go over the types of errors. The first type of error is where we reject the null. That is, we say, yes, there's a difference. So remember, when we reject the null hypothesis is the answer that says there's no difference. So if we reject the null, we say, yes, there's a difference. But it turns out it's actually true. So that means we decide that there is a difference, but the situation, what happened on the day of the test, or test day, is there was no difference. So in that case, then, our decision is wrong. It turned out to be wrong. And that's a type 1 error. So in more everyday English, we make a type 1 error when we say there is a difference when there actually is none. So there is a probability of us making this error. And generally, we want to make less of this, like a lot less. So again, in a population, let's say of 100, if we want to pick, one person that had the prize again, we want to reduce our chances of getting it wrong. So, for example, this would mean, okay, if we could eliminate options, so like instead of choosing one person from 100, maybe we want to choose maybe one from 50, or one from 20, one from 10, or one from 5. So every time we reduce that probability, we are less likely to make that error. So in terms of the null distribution, if we make a decision at exactly the mean, well, that means, we draw from anywhere, like 1 from 100. That means we're going to make a wrong choice or wrong decision every time. But as we choose more extreme critical values to make our decision, instead of plus or minus 1, we go plus or minus 2. So we eliminate our options in terms of rejecting the null. We are reducing our probability of making that wrong type 1 error decision. So it would be like, it's a lot easier to pick 1 out of 5 people versus picking 1 out of 100 people. So for us to decide, based on the sampling distribution or null distribution, that whether the sample mean is far enough from the population mean for us to say there's a difference, then by increasing the extreme critical value to 2 standard deviations away, or even 3 standard deviations away, we are reducing that probability to 5% or even 1%. So it becomes very unlikely for that sample mean to be the same as the population mean within the sampling distribution of sample means. So alpha here in notation would be the probability of a type 1 error. So that's what you might see in your notation in either this class or other classes once we start talking about alpha. One thing about alpha is that it is arbitrary. In the context of this course and up many levels, we would say that, yeah, we want it low for sure, but whatever value it is, there are commonly accepted values like 5%, 1%, even 10%, or even 0.5%. what determines the alpha level often is the stakes. Like, for example, do you really, really, really want to be extra, extra careful? So let's say if it was a vaccine or a drug that's supposed to treat a serious illness, you really want to make sure it works. So you really don't want to make a false decision. Therefore, you could really reduce the alpha level and increase the critical value to some extreme. Z-score and some really low probability. It could be 1% or 0.5%. If the stakes were lower, let's say you're trying to compare a difference between the taste of one apple to another, the stakes are lower, but you want to see if there's a difference, well, maybe 5% or 10% would be sufficient given the stakes. However, again, you want to keep your alpha low. Anything that's 20% or more will start to make a lot less sense, because you're probably going to make a wrong decision saying there is a difference when there is no difference every time. One other term for this type 1 error would be a false positive. Positive here meaning, oh yeah, I found something, or I found the difference. Like a positive result. Not to say there is a positive change in direction or difference, but it's just one sort of English way of saying, oh, we think we found a difference, but there it really isn't. The opposite error then would be to say, oh, we failed to reject the null when it was actually false. That is, we say there is no difference when there actually is one. So logically, if type 1 says it's a false positive where we say there's a difference when there really isn't, the opposite error you could make then is to say there is no difference when there actually is one. Again, once you understand at least the first one, the type 1 error, logically type 2 error is the opposite. So it makes it a little easier to understand, and it makes my explanation a lot shorter. So another term for this would be a false negative. Again, negative would be like negative effect, negative difference. We don't think there is, but that's actually not true. Note, however, the probability of making a type 2 error is a lot harder to actually calculate and identify or even define. There are reasons for this, and that includes calculating power. That is the power, the probability of detecting a difference between either one sample to another or the sample to the population within a sampling distribution. But for now, we can say in this chapter, in this course, that type 2 error is when we make a false negative. That is, we fail to reject the null, saying there is no difference when there actually is one. Okay? So, taken together then, we can make two types of errors, type 1 and type 2. And this decision-making matrix is something that you can practice on your own in drawing. There are probably going to be questions that would either be a definition that they could ask you. They could ask you about what a type 1 error is or what a type 2 error is. Or they might start throwing application questions at you and say, oh, well, a pharmaceutical company said this drug has an effect, but there actually isn't one. Well, what type of error is that? Or in a court, the jury decided that the person was innocent, but the defendant actually committed the crime. Well, what type of error was that? So again, a way for you to make sure you understand the types of errors you could make in hypothesis testing, you need to know at least two things as you describe the types of errors. One, you need to know what decisions you could make. You could either reject or fail to reject the null, and that is the null hypothesis. We don't work with the alternative or research hypothesis here. The other thing you want to know is that, the null hypothesis could be true. That means there actually is no effect. This is not decision. This is what is actually happening in the world at that moment when you were doing your test. Or the null hypothesis could turn out to be false. So some effect actually exists. Usually we're talking about the treatment effect because we're testing for that. So when we match our decision with the situation, then we make the correct decision. So when there is no difference on test day in the situation, when the null is true. We fail to reject it, that is correct. When the null is false and there is a difference from the sample that we've drawn from the population, and we reject the null based on the sampling distribution or the null distribution, yeah, we make the correct decision also. However, things can go wrong for us in terms of our decision when if the null was true and we reject the null, or we can say it this way, we reject the null, we decide there is no difference when there actually is one, that's type 1 error. Alpha here again is the probability of a type 1 error. Usually you just write type 1, and if you're taking a stats class or you're reading this, you would know this is type 1 error. It's not type 1 anything else here. Accordingly, then, if you fail to reject the null when the null is false, we decide that there is a difference when there actually isn't one, then this is beta. And this is your probability of making a type 2 error. Now, when we apply the 100% rule or property in probabilities, then we can figure out how to put probability values in the other outcomes, that is the correct decisions. So let's take a look. When the null is true and we reject it, that is, we say there is a difference when there isn't one, that's incorrect. That's a type 1 error. But if we fail to reject the null when there is no difference, that is a correct decision, and therefore this would be 1 minus alpha. That is the probability of correctly failing to reject the null, or correctly saying that there is no difference. Now, the other correct decision then has its own probability too, and that is 1 minus beta. That is when the null is false and we reject the null. That is, there is a difference and we reject the null saying there is a difference. Then that is, 1 minus beta, and that's the probability of correctly rejecting the null, which I'll just write as correct rejection. Now, there's a special term for this correct decision, and particularly this type of correct rejection of the null, this correct positive. Because in research, yes, we are supposed to train ourselves to test the null hypothesis, but really we're trying to see if the treatment has an effect, whether the treatment makes a difference. So therefore, the term for this, and we'll see this in our end of this chapter as we talk about power, the term is power. That is specifically the power for a statistical test to detect an effect or a difference. One quick way to think about this is the power of a magnifying glass or a microscope. That is, our naked eye can't tell minute differences between two objects, and these are going to be two very small objects, like 2 dots. So for example, if I draw 2 dots like this, you can probably see a difference, but on your screen on YouTube you might not be able to, versus where I draw something like this. Let's say instead of me making the distance further, let's say I increase the scale. So let's say if this was 1x, here is probably maybe about 10x, 10 times as much. So there are factors that affect the power here. That is the probability of us to correctly reject the null. And one of those things would be sample size. Because sample size, if you remember, directly affects standard error in a sampling distribution. So again, between the sampling distribution and our sample distribution, then if the distributions are tighter more tightly packed together, then there's fewer overlap between the two distributions. Specifically, if we compare two populations, even if it's the treated sample where we're trying to see if that sample is from a different population, then this alternative distribution where the null is false, and here the sampling distribution where the null is true, if the sampling distribution has a smaller standard error as determined by the larger sample size, then there's fewer overlap, and that's going to increase the probability of us saying that there is a difference between two means, that is the population mean and the sample mean, when they're further apart. So going back to our critical region boundaries, we are going back to dealing with type 1 error. That is alpha. Again, alpha is the probability of making type 1 error. Again, we want to keep those probabilities small. So we're going to talk about power much later on, and here we're going to first talk about type 1 error. That is alpha. So as you can see, these are the values that researchers most often set, particularly 0.5 or 0.01. That is 5% or 1%. Here is going to be even smaller. This is going to be 0.1%. In terms of standard deviations away from the mean, here, that this would be a null distribution in this case. Definitely a sampling distribution. Transformed into z-scores. Then 5% would be almost 2 standard deviations away. 1% would be 2.5, a little bit more than 2.5 standard deviations away. And 0.1% would be 3 1/3 almost standard deviations away. So each of these then, if this was a two-tail test, whether when we're just trying to see if there's a difference, for alpha at 0.05, then each tail would have 0.025, which is 2.5%. Here, if alpha is set at 0.01, each tail would have, for a two-tail test, 0.005, which is 0.5%. And here, this last one, which is very extreme, the mean would be, if a sample mean was located near, it would be considered extremely unlikely that it would be 0.0005. That is 0.05%. Again, for each tail in a two-tail test. Two-tail tests are used when, you're trying to see if there is a difference. It could be positive or negative. So one thing to note here then is that a two-tail test, when the alpha is split in half, 1/2 for each tail, the critical value is larger than if it was a one-tail test, where we'll talk about it near the end. For example, alpha then would be the same, let's say if it was 0.5, but instead of splitting it in half, you have 0.5 for one tail. Therefore, the Z value here would be lower than 1.96. In fact, it would be 1.645. Again, that would be for one tail test, and we'll go over this in more detail when we do our one tail test section. But for now, we're going to say that, yeah, the alpha is going to be split in a sampling distribution when we're simply trying to look for a difference. Again, it could be positive or negative. Therefore, one thing to note, the critical regions for a two-tail test is going to be smaller in each tail than it is for a one-tail test, where you're looking for a either increase or decrease in the sample mean compared to the population mean. Like whether there is an increase in something or a decrease in something. It could be performance or risk or whatever. So to review here, you can set your alpha at the percentage that you would commonly use. It could be 5% or 1%. Usually we use 5% in this course. So if it was a one-tail test, then you would see, oh, the Z value, the critical value for alpha would be, well, in the unit normal table, we would have the tail here is 0.0505 and 0.0495. So we average those two. And so the Z value is 1.64. So we choose for one tail test 1.645. So there's no plus or minus here. It's a one tail test. All of the alpha would be used in one tail. Therefore, it would either be positive 1.645 if we're looking for an increase in effect, or negative 1.645 for a 5% alpha if we want if we're looking for a decrease. And we would decide this or set this rule before we collect the data. And we set our alpha. That is our probability of a type 1 error. Not increase, but decrease in the alternative hypothesis. So let's try some concept and application questions for type 1 and type 2 error. So starting with this question, that's two parts. A type 1 error is like convicting an innocent person in a jury trial. Notice this is an application question using a courtroom example. See if you would say this statement is true or false. And B, a type 2 error is like convicting a guilty person in a jury trial. So take a moment and think about it. You can use the decision matrix and put in the courtroom decision if you like. So for example, here the null would be innocent. So let's say null is true. So you would say not guilty or innocent. Guilty or innocent. And then here we say guilty. Well, guilty is guilty. So we'll leave that there. And then we reject the null. Then here we convict the person. And we fail to reject the null. That means, oh, okay, we say the person is not guilty. So the word here would be to acquit the person. It's different from pardon, but that's going to be something about for the law. But anyway, failing to reject the null is to say that the person is not guilty. So again, you can use this to help you figure out whether your decision to convict or acquit, in this case, both questions talk about convicting a person or the defendant, and in the case, the defendant is either guilty or not guilty. So going back to the question then, if you answered true for the first statement, you would be correct. Again, the decision is to convict the person, the defendant, and the defendant happens to be innocent. Therefore, you have made an error if you have decided to convict this person in a court of law as a jury member, as part of a jury. And so, yeah, it would be a false positive. And yes, it is to wrongly reject the null. For statement B, if you answered false, well, that's correct because the statement itself is not correct. That is, well, a type 2 error would be to say that the guilty person is actually innocent. So it's the decision that is matching. If the decision matches the actual outcome, then it's not an error at all. So you need to review the definition of the type 2 error. That is to falsely acquit a person. That is to falsely say that the guilty person or the person who happens to actually commit the crime, and say that person is innocent. Okay. So again, working with these practice questions in terms of decision and the situation would help you figure out what alpha, beta, and power is, as well as the types of errors that a researcher could make. So to review, the 4 steps of hypothesis testing are: 1, to state your hypotheses, that is your null hypothesis and your research hypothesis. You'd also select your alpha level as you locate your critical regions. Again, alpha usually would be at either 0.05 or 0.01. There are other alpha levels that a researcher could set, but these are the most common, at least for this course and this level. Again, depending on what your alternative hypothesis is, depending on what type of effect you're looking for, you would also decide whether the alpha level, the critical region that you're going to set, is either going to be one-tailed or two-tailed. In many cases, if not most cases, the researcher would be simply look for a difference, and therefore the alpha would be split in half. If you're looking for either a increase or decrease, then the entire tail, this will be a one-tail test, would hold all of alpha. Therefore, your critical values then would change depending on how large your critical region is, because the critical value is the location where if the sample mean is beyond that critical value, that is more extreme, then you would reject the null. So you would set your regions and say reject or fail to reject. Whether it's a one-tail test or a two-tail test, you would set your critical regions, have your critical values, and then make your rules, your decision rules. So the line right here where you set your critical region, that is going to be your critical value. And for this particular chapter in this test, these are Z values, so we call them Z crit, or critical value. In step 3, we collect data and compute a test statistic, and that test statistic would be, again, because we're working with Z values, that would be your Z observed. And then your critical value would be, again, because we're working with Z scores right now, Z crit. If your test statistic is more extreme than your critical value, if the critical value is in the positive direction and your test statistic is more extreme than that, so for example, if it was 2 in a plus 1.96, it could be plus or minus. In this case, it would be, if alpha is set at 0.05. Then, yeah, if you find a Z score of 2.0, that would be more extreme. Therefore, you would reject the null. If it was less extreme, let's say 1.0, or even something, even if it was 1.95, then now it's less extreme. And therefore, you would fail to reject the null. So your decision-making rules come first after stating your hypotheses, selecting your alpha level, setting your critical regions, figuring out if it's one-tail or two-tail, depending on what your alternative hypothesis is, and then your test statistic would tell you what decision you should make. So if you make a decision based on the statistical evidence that you got from your test statistic, the observed value, compare it with the critical value, and you say, oh yeah, it's more extreme, I'm going to decide to reject the null, then a common term you would use in research is to say that result, that is the observed result, is statistically significant. Significant here means that it's extreme, the sample mean is extreme enough, that the observed statistic is extreme enough that you decide to say that there is a difference. That is, you decide to reject the null. A significant result in research. Here, statistically significant is not the same as practically significant. Well, that's going to be the effect size. That is, we can say there is a difference, but is that difference going to be large enough for us to see an actual impact, practically speaking? But statistically, in the sampling distribution, we say, oh yeah, the sample mean is far enough. So that's separate. We test for a difference first before we determine the magnitude of the difference. So here we say statistically significant, but it's enough for us to say we reject the null based on statistic or statistical evidence. So that's what we'll see in the literature as well. So when you read research articles, so this could be in your Psych 217 class if you're taking it in Alexander College in research methods, or you might have seen it before or heard it before in the news or in other articles. Maybe you've heard it or read about it in your articles in your Psych first level Psych class, your intro to Psych 1 and 2 maybe. So again, those are the words that are used. Significance, again, that is to say your test statistic, your observed value is more extreme than the critical value for us to decide to reject the null hypothesis. So that's what that says. In your articles, or when you use statistical procedures and conduct research and analyze the behavioral data and make inferences, then we report the value of the test statistic, that is our observed value. In this chapter, it would be Z observed. In the next chapter, it would be T observed. And in other chapters, we'll have a different value. And we'll talk about that. If you're using some program tool where you could calculate the p-value, or if you find the corresponding value in the unit normal table, often there's a difference there. If you find a observed statistic and you find the critical and you find this corresponding tail probability, in this unit normal table, you're going to get 3 decimal points. But if you happen to use some tool, and there are these going around and they're very useful for you to practice and do your own research. But if you happen to use those in the test and you just state the p-value, and they end up as being more than 3 decimal points, or you state the p-value without saying what the observed statistic is, then chances are you probably just used the software, which means you didn't really do the steps, which means in this course, you haven't done the work. So in your report, yes, you would report the p-value, and you could use the software, but in this course, you would report the observed statistic, and you could try and find the corresponding p-value in the tail section that corresponds to the Z statistic in this chapter when you're working with Z scores. But if you happen to use only the p-value and it's so precise, or you report only the p-value without the observed statistic, chances are you're cheating, or you're using just the software, which isn't what we're supposed to do in this class. Again, the 4 steps, we want you to follow those so then you can complete the whole process in your own research methods class as well. So of course, we would want to also report our decision to reject the null as well. So this is a picture of what you would do to set your critical region in a standard test. Here is going to be a Z test because we're working with population data that is known to us, and so things like the population mean and the population standard deviation. Therefore, we can use Z scores and set up a sampling distribution where the null is true, and these will be a distribution of Z scores. The mean is here. We set some critical region with some critical values. Here you can see is a two-tail test. Therefore, the alpha is split into 2. So if we set alpha here at 0.05, here the alpha would be 0.025. And you would do really well to write these down too as you make your critical region. So you would actually write out the sampling distribution, that is the null distribution. Say that the null is true to indicate that this is a null distribution. Set your set scores, so set for 0 being the mean. Determine your critical regions. Again, for now we're starting with a two-tailed test, so we split alpha in half. And then we would make our decisions. So it would be, let's say here, well, that's pretty easy, 1.96, because once you've done enough of these, you know the values for certain alphas and its corresponding z-score. And then you would set your decision rules. Again, for the first couple times, just recommend that you write in full. So I'm going to do that as well. Fail to reject no. As you do more and more of these, you might find, I'm getting bored or I'm getting tired of writing the whole word. So you could write F2R, for example. But again, as long as you practice enough and you're consistent in your critical region, doing all the steps, including the null distribution, your alpha, what is set as, whether you need to split the alpha into 2 for a two-tailed test, find your critical value for each part of the tail, or each tail, and then write your decision rules. Which part do I reject the null? Which parts do I fail to reject? Then you're okay. And that's step 2. There are other assumptions you want to make when you make and do your hypothesis testing as well. Again, because we're working with our sampling distribution, the first assumption we're going to make, well, the sample is randomly selected. And if there was a treatment group, then the treatment group is randomly assigned. Again, random here means that each person from the population has an equal probability or equal chance of being selected. That's very important. We want the sample to be representative of the population as much as we can. Next, these observations are independent. That is, that each score, each participant is independent from other participants, like all of them. Like as if it was research, you do one participant at a time and they're not put in together in such a way that, one person is going to affect the other. That would be a confound, a confounding variable. So if that term is familiar to you, you probably took that in a research methods class or heard about it in your first year level psych. But that means, again, we want to control for all the other factors, and in hypothesis testing, we're testing for the treatment effect. So the observations here are independent. That is also leads to the next point. The variance here and the standard deviation of the population is not changed by the treatment. That is, well, we're gathering sample from the same population, but the only change that the treatment would do is it would either increase or decrease the scores of the sample in such a way that, we're trying to determine if the increase or decrease or the change is going to change those scores as a whole. But again, we wouldn't expect the treatment to change the variability of the sample. If it does, then it would be another confound, because, well, what would that mean? Logically, that would mean, well, the treatment might make some people score higher and some people score lower. Well, then is the treatment really doing anything, or is it also quote unquote random? If the treatment really works, then it would do one thing for everybody. Either it would increase all the scores or decrease all the scores in the sample. Finally, the sampling distribution, that is the null distribution which we use to test our sample or test the sample against, would also be normally distributed. And remember from last chapter how we can assume the normal distribution of the sampling distribution. That is, well, 1, the sample is large enough, 30 or more. 2, the population distribution itself is also normally distributed. So those are the assumptions we would make for hypothesis testing. In this course, the assumptions are sort of given because we want you to focus more on the steps of hypothesis testing. But as you take more advanced courses, these assumptions themselves would be tested, because in real life, maybe the population isn't normally distributed. Maybe your sample isn't large enough. Maybe the treatment does increase the variance somehow. Maybe there's inconsistent testing, or the researchers themselves are not consistent. Maybe that would lead to things like inter-rater reliability, or the observations themselves may one person could affect another. So these assumptions could be violated, and therefore if enough of these assumptions are violated, even if it's just one, if that assumption is really violated, that means you might not be able to do the hypothesis testing in the first place. But for this course and this chapter, we're going to say, yeah, these assumptions are not violated. We're going to say, yeah, we can assume random sampling, we can assume independent observation, we can assume that the population standard deviation doesn't change by the treatment, and we can assume that the sampling distribution is normally distributed, and then we just conduct the test. Other factors that influence hypothesis testing, these would be sort of a good to know, especially if you continue on with statistics, is that the size of the difference between the mean, and that is the original population mean, and the sample mean, then the larger the difference between those means, you'll have a larger Z-score. Makes sense. It's a more extreme value, and Z-score is a location score. Also, the variability also influences hypothesis testing. It also influences your decision as well. Again, if the scores are more tightly packed, then you would have less overlap between the two distributions. And so you look at the means, they're definitely apart, but also because there's no overlap, the lowest value of one distribution and the highest value of the other distribution, they don't touch at all. Well, then you can really say, well, those distributions are really different. But if the distributions have overlap, that means more variability between your null distribution and your alternative distribution. Then there's overlap, then it's much harder, quote unquote, for us to say if there is a difference, because the two distributions have scores that overlap one another. Well, it would be like saying if two classes, like one class, like I teach one class and another instructor teaches another class, and then our scores just overlap. Like you can have people scoring in the whole range of, like, let's say 50 to 90% for both classes. Then can we say both classes are different in terms of their scores? Not really. But if one instructor is really easy and one instructor is really hard, and the students either consistently get a low score or consistently get a high score, and they're from different classes, then you can say, yeah, there's a difference between those two classes. Also, the number of scores in the sample would directly influence the variability of the scores, particularly your standard error. The larger your sample size, the smaller the standard error. So those are your factors. The difference between the sample mean and the population mean, the variability of the scores, that is directly influenced by your number of scores in the sample. So here's another learning check. Question 5, multiple choice. A researcher uses the hypothesis test to determine whether do subscript here. No, I can't. That's okay. I'll do it later. To determine whether there's a difference. And so the null hypothesis says, oh, well, the population mean here is 80. So then you would expect the sample to also get a sample mean of around 80. In this case then, the question is, which combination of factors, and you can go back to the previous slide for this in terms of influences, would lead the researcher to reject the null? So what is the most likely combination of what is the combination of factors that would be most likely for the researcher to go, yeah, I'm going to reject the null? So compare the possible factors here. 1, A, you have a standard deviation of 5 and a sample size of 25. C is, well, the same standard deviation of 5, but a sample size that is larger. C, the standard deviation is larger now, 10, and the sample size is 25, the smaller one. And D, standard deviation of 10 with a sample size of 50. Take a moment and think about it. How standard error is influenced by sample size and what happens to your hypothesis testing when the standard deviation of the population is also larger or smaller. So if you have chosen the one that has the smallest standard deviation for the population and the largest sample size, which means the smallest standard error, then you are correct. Next learning check question. Again, true, false, 2 parts. 1. An effect that exists is more likely to be detected if n is large. True or false? Second, an effect that exists is less likely to be detected if sigma, that is population standard deviation, is large. Again, think about this as well in terms of standard error, because we're looking at n, and population standard deviation, because we're looking at sigma, and how those influence our hypothesis testing. Both of these statements are true. Again, if n is large, our sample size is large, we produce a smaller standard error. Therefore, the sample means are going to be more tightly packed towards the mean. So instead of some sampling distribution that is fatter and flatter, shorter and wider, you're going to get a sampling distribution that is taller and thinner. Both of these could be the null distribution, but again, your sample size here, let's say this is n equals, 10, and this one would be n equals 50. And your standard error here would be, that's sigma, not. And so the same z-score then would be in a different location. The same sample mean would be in a different location, would have a different z-score as well, in the sampling distribution, depending on what it is that is influenced by the sample size. So again, a sampling distribution with a smaller standard error is going to be more likely for the researcher for you to detect an effect. Conversely, if the population standard deviation itself is larger, then you're going to increase standard error because, again, there's 2 ways of looking at this. One, the standard error formula tells us, well, we need the population standard deviation first. And logically, again, if you have a population distribution that has a large spread, like even the range is larger, the sample means that you could get would be more extreme as well. And therefore, you're going to get a z-score that is going to be smaller because the population distribution itself is larger in the first place. So both of these statements are true. So the last bit we're going to cover then, before we finish part 2, is the idea of directional hypothesis tests. That is, well, instead of trying to see if there's simply a difference, whether the sample mean could be larger or smaller than the population mean, we're specifically looking for one direction. That is, we're trying to say if the sample mean or the treatment is going to increase or decrease the target behavior, rather than just saying if there is any difference. So in terms of drawing your critical region, as well as stating your hypothesis, your critical region for a two-tailed test would look like this, and your alpha would be split into 2. Again, this is the null distribution with its own mean transformed into z-score. And then you have two regions where you would reject the null. I'm just going to use shorthand here. Here, the alternative hypothesis would be, well, if it was a population mean, then it would not equal some value. For now, I'll just say 0. However, if we start looking for directional tests where we look for an increase or decrease, well, alpha is no longer split, so this whole thing is alpha. And again, we're working with a null distribution. And so we have one region where we reject the null, and the other region would be failing to reject the null. And the alternative hypothesis for a positive directional test, a right tail test, notice the tail is at the right. For example, it could be 0.05, 0.02, 0.05. Whereas in a two-tail test, it will be 0.025. Again, it's a good idea to write those out in your region, critical regions as well. Here it would be, well, oh, I'm looking for something larger. There you go. Mu here is larger than 0. On the other hand, or other tail, haha, you're looking for a decrease, well, the tail is going to be on the left. The null is true. This is the sampling distribution with its own mean. Again, the left tail is going to be a rejection region, and everything else, the body, is going to be your failure to reject region. And your alternative hypothesis then would be, well, less than 0. Again, I'm using 0 as an example here. It could be anything. It would be the population mean that you're looking at. So I'm just going to say, put a value of 50 because we've seen that value before. Again, the value of the population mean would be determined by the question. So when you set your alternative hypothesis, if it's just simply looking for a difference, again, it could be positive or negative. Therefore, it's non-directional, two-tailed. In your alternative hypothesis, just put the not equal sign. If you're looking for directional tests, an increase would have you using the greater than sign, and a decrease would have you using the less than sign. The fun part here is that for your null hypothesis, if you use a right tail test, your null hypothesis would say the opposite. So that would be less than or equal to the population mean value. Notice here it's the opposite of your alternative hypothesis. And if you're using a left tail test, then you would write for the null hypothesis, mu is greater than or equal to, again, well, not 0, 50, because that's the value we're using. So again, if you're using a one-directional test, or one-tail test, then the null hypothesis is the opposite, including the opposite direction. So you could say null difference as well as, the opposite direction. So if you're looking for an increase where it would improve something, well, if you find a sample mean that is worse, then that would be part of the null hypothesis as well. Conversely, if you're looking for a decrease, well, it could be like reducing risk, and it turns out the sample mean shows greater risk, well, then it's part of that null hypothesis. So that's something to keep in mind when you do directional tests. And the key thing for students and even researchers for determining whether you want to do a non-directional test or a directional test is the research question and your hypothesis. Are you simply looking for a difference? Then use a two-tail test. Are you looking for a specific increase or decrease? Then use a directional test and state the specific alternative hypothesis and then work out your null hypothesis. That is everything else. So the next slide talks about this in point form. Your directional hypothesis test has a specific direction of treatment. Again, it could be a right tail test, and this would be a right tail test. Or it could be a left tail test where you're looking for a decrease. So it's either or too, by the way. Yeah, you can't look for both increase or decrease. If you are, then you're just trying to look for a difference, and then you'll use a non-directional test. Again, to review, your null hypothesis, depending on which tail test you're doing, would be the opposite, whatever is left. So if you're looking for an increase, your alternative hypothesis would say the mu is greater than the value, the population mean. Then the null hypothesis would be everything else, less than or equal to that population mean. If you're working with a left tail test looking for a decrease, well, the null hypothesis for that would be, well, mu is greater than or equal to the value of the population. In our course, in this case, it will be given by the question or in your practice questions. So in the next slide, then you'll see an example of a one-directional test. Specifically, well, here it's going to be 1.645, but the slide here shows 1.65, which is, for this context, is close enough. But you want to use the exact value whenever possible. Notice here then, this whole area, because it's a directional test and it's an increase, here the distribution is the null distribution. And to review, your alternative hypothesis would be, well, mu is, well, we have the value right here, so it's greater than 80. Alpha here is 0.05, that is 5%. This whole thing is alpha, by the way, which is 5% or 0.05. In this area, in this region, we would reject the null. And in everything else, in the body section, we would fail to reject the null. And for clarity's sake, I'm going to write it in the same line like that. And of course, don't forget to write your null hypothesis. Again, it's the body. So you can see this right here. Well, it's less than or equal to 80. Okay? Don't get confused about the critical value. The hypothesis itself is written first. So this is step 1. Then you set your critical region in step 2 using the null distribution with the mean here and then the standard error. And then you state your region based on what test you're doing. This will be a right tail test where alpha is all one tail, the whole 5% if we set alpha at 0.05 to be in that direction. So that's what it looks like for a directional test. If it was the opposite, well then alpha would be on this side in a left tail test. And the values would change. So, or the hypotheses would change. The alternative then would be less than 80. And the null then here would be greater than or equal to 80 if it was for a left tail test like that. So the next slide then would help us distinguish between a one-tail or a two-tail test. So if you got lost in the explanations that we were providing in the video, this slide then, when you review it, should help you make sure that you're able to distinguish between a one-tail or two-tail test. In the points here, you'll see that a one-tail test allows for rejecting the null in a particular direction. Whereas a two-tail test would be both directions. So the bit that says whether it's a large difference here. This difference here is specifically referring to the difference between the sample mean and the population mean. And because the critical region in a one-tailed test is by default twice as large as the critical region for a two-tailed test. So remember, if alpha was 0.05, the whole tail for one-directional test or one-tailed test would be the whole alpha. In this case, the whole 5%. Whereas if it was a two-tailed test, the alpha is split in half by default. Therefore, it is, for example, if it was alpha set at 0.05, then each half would be 0.025. Therefore, the observed statistic needs to be more extreme. That is the difference between the mean and the population mean, that is the sample mean and the population mean, needs to be larger in a two-tailed test for the researcher to reject the null. Therefore, in that case, in general, you should use a two-tailed test because you're reducing the probability of a type 1 error because you're dividing the critical region in half. And both halves add to alpha. That is the probability of a type 1 error that you set beforehand. So the last bit reads, unless you have a strong justification, that is, you really are expecting a positive or negative difference here, that is an increase or decrease, like maybe you've done the test before, maybe you're replicating the research, like the first research, was simply looking for a difference and it was already very extreme. And so when you replicate it, maybe it makes a difference, you're trying to test it again. That might be one case of a stronger justification. Otherwise, if you're doing a pilot study, if you don't know, you have less of a justification, you should use a two-tailed test. That reduces your probability of making a type 1 error, and the test itself would require a more extreme value, a larger difference, for us to reject the null. So that's some differences there. And you're going to see questions like that, at least for your test, for us to test your application and your understanding of how one-tailed tests and two-tailed tests are different and when you should use one versus the other. So the last bit of learning check for this part, I think. So, multiple choice, question 7. A researcher is predicting that a treatment will decrease scores. So here you're going to want to read the question carefully about what is happening and what the researcher wants to do. If the treatment is evaluated with a directional hypothesis test, and you're probably thinking one-tailed test, then you're right. Then the critical region of the test, fill in the best answer here. A would be entirely in the right tail direction. B would be entirely in the left tail direction. C would be equally divided between two tails of the distribution. Or D, you can't answer this question without knowing alpha. Take a moment and think about this, about how one-tail tests work depending on the research question. That is your alternative hypothesis, or your answer to your research question as stated in the alternative or research hypothesis, and see what the best answer for this question would be. If you've chosen B, the left tail direction in the distribution, you're right. Well, because the researcher is looking for a decrease, therefore it's going to be lower than the population mean, therefore it's going to be on the left hand side of the distribution, therefore it's going to be on the left tail. So that's it then for part 2 of our hypothesis testing. This is definitely one of our longer lecture slides and longer chapters. One reason for this is, well, hypothesis testing is the foundation of inferential statistics. Without this tool, without the steps for us to use this tool, we can't consistently and reliably compare samples with populations. We can't answer research questions. We can't test answers to research questions, that is hypothesis. And we can't analyze behavioral data beyond descriptive statistics. We can't make inferences about the population. We can't compare samples. We can't compare sample with population, and so on. So again, when you review hypothesis testing, make sure you not only know the steps and you're able to do each step accurately and in the right order. Make sure you are aware now in part 2 what the errors you could make are, what are the correct decisions, and how you would decide and when you would decide to use a one-tailed test or a two-tailed test, and what differences and implications those tests would have. So again, make sure you practice using your textbook questions. Make sure you practice using your web tutorials. And if you still got questions after that, you can email me directly if you're taking this class in the college that I'm teaching at. In this case, it's Alexander College when I'm recording this video. Again, keep going. Make sure you practice with the resources, and we'll see you in the next one.